Dr. Paul Shea will be telling us about his Deepwater Horizon oil spill experience, and Andrew Dunning bringing us the geology news. Welcome to Geology Talk, our monthly gathering of geology enthusiasts, brought to you by the Geological Society of the Oregon Country and the Beverly Vote Scholarship Fund. And hey, it was our our third birthday. And actually, it turns out it was in April, but when I was doing this video montage and I went back and looked at our past videos, 3 years worth, I discovered that our first video was actually April of 2020, when, like a lot of other organizations, we had to suddenly scramble to create programming to fill the void in our in-person. And our first presentation was from Professor Alston, her Assembling Oregon. You can see that on our YouTube channel. But thank you for everyone. Some of you have been here all 3 years, and we really appreciate that. And we've got lots of great content going forward. So this is really our 4th year. Our panelists today, Andrew Dunning, Emma Rahalski, Carrie Gordon, and myself, and our wonderful technical director, Gary Joquin, in the background. I think that's all I have in the way of geological announcements. I'm going to stop sharing my screen and ask Emma, you weren't here last month. What were you doing?
Yeah, so as some of you know, I'm interested in karst geology, which is the landforms that happen in a type of rock, carbonate rocks. They dissolve really easily and they form caves. So I'm really into caving, and I recently joined the Oregon Grotto and was planning on going on a beginner's trip, caving trip to learn some caving skills. That was unfortunately canceled because we've had a lot of snow this past winter, so the cave that we were planning on going to was inaccessible. But in place of that, I went to the Oregon High Desert Grottos vertical practice, which was hosted in Redmond, Oregon. So we learned how to basically do a bunch of rope work so that you can ascend and descend in caves. And yeah, for anybody who's interested in caving, I highly recommend checking out local grottos, because they host a lot of caving trips and they're very active. So the Oregon Grotto is in the Portland area, but the High Desert Grotto does more central Oregon stuff. So
In the Oregon Grotto, that's at Rocky Butte, is it not?
oh, that's a different spot.
That's
So
a different grotto.
that is just the grotto. Yeah,
Okay.
but the Oregon Grotto is a club. So
Okay.
they meet monthly. Up in the last meeting was up in Vancouver, Washington, at a round table. But yeah, they do mostly caving excursions closer to the Portland area. But there's a lot of overlap between grottos. And for those who don't live in Oregon, if you just look up grotto in your local area, you can find a lot of good caving clubs.
You'll find a society. And you're going to be bringing us a presentation next month as well.
Yeah, so I'm wrapping up my my undergraduate degree at Portland State, and I'm doing a senior thesis studying the water at the Oregon caves. We're doing a stable isotope study, which, for those who don't know what that is, you'll learn if you come to the talk next month. But I'll be giving a presentation about the findings of my senior thesis and my trip to the Oregon caves, which was really cool. So,
wonderful. That's exciting. And thank you, Emma. Well, Andrew, are you ready for the geology news?
I sure am.
Okay.
All right, this is the geology news for May of 2023. Some interesting stuff going on, a lot of it local, so let's get into that. Starting with earthquakes as usual, we got a magnitude 7.7 south of the Loyalty Islands here in the South Pacific. This is the largest event of the last 30 days globally. It was a subduction zone earthquake, but it was not a megathrust event like we would expect from a Cascadia subduction zone, or like we see in Japan, Chile, Alaska, Sumatra, et cetera, et cetera, et cetera. This is a normal fault earthquake, which is more what you'd see in somewhere like Nevada, where you get tension. This is an extensional earthquake. As this subducting plate goes underneath the Australian plate, there's a point of flexure, and that's where you get normal earthquakes, where you get this kind of extension. So that's a large flexural earthquake, and that's kind of interesting. There was another earthquake nearby, 7.6 outside of Tonga, also in the South Pacific. But this is a very different earthquake. It's called a deep focus earthquake, so it's 200 kilometers below the surface. For comparison, this 7.7 I mentioned is, actually did not write down the actual number, but it's probably in the neighborhood of 20 to 30 kilometers deep. So this is, 10 times deeper than that. And the mechanisms for why these deep focus earthquakes happen is a matter of, frankly, speculation and ongoing research. So that's kind of cool. Here in the United States, we had for me, a good earthquake month. We had a magnitude 5 in Lake Almanor, California, which is here in the northern Sierra Nevada mountains. This is a strike slip earthquake, which is related to the San Andreas Fault, as it squishes the entire western part of North America and causes faults to rupture between the Pacific Ocean and the Wasatch Front in Utah. This was followed by a magnitude 5.2 several days later, just before I flew down to Reno for the GSA Cordilleran section. That's the Geological Society of America section for international and Western states, which was a lot of fun. That was a great conference. Also in California this last month, there were 2 earthquakes, about a magnitude 4 here in the Imperial Valley, most seismically active place on the west, and 1 magnitude 4 at the very northern end of Death Valley, one of my favorite places. Overall, very interesting. No unusual or terribly interesting activity, just earthquakes in places I think are cool. As for global volcanic activity, there are 28 ongoing or new volcanic eruptions with substantial activity at Rincon de la Vieja in Costa Rica, number of steam explosions and pyroclastic flows, which are density currents, basically superheated many hundreds of degrees Celsius dust clouds that roar down the slopes of the volcano. And over here in central Mexico, looming above Mexico City, Popocatépetl has renewed activity. It's been dormant since 2017. It is the largest and most hazardous volcano in Mexico. It's 17,800 feet tall, looms over Mexico City, and this is the smaller city of Puebla, which has been seeing ash fall from the smaller steam explosions at Popocatépetl. This is what that vent looks like as viewed by one of the local volcano observatories. So nothing major. Some flights have had to be rerouted, but overall, nothing like previous eruptive activity so far, which can be quite challenging from such a large volcano. Any questions about those sorts of things before I move on?
Actually, there was a question about GSA membership. Would you recommend that to non-geologists, laymen's? Are there any benefits to them?
If you want, it's mostly research scientists, and if you go to those events, they are mostly not geared for public engagement. There are non-geologists who do go to those, including some GSOC members. But if I wasn't a full-time geologist, I would probably seek a different enthusiasts organization that is more geared toward public members.
Yeah, my experience with GSA is you need to have your geologic dictionary close at hand sometimes. I do have a question. How old is Popocatépetl? Because I seem to recall it's not that old of a volcano.
No, I mean, just look at its shape. It's clearly not been too long-lived, but this horn here, this pointy prominence, is remnants of an older volcano. So volcanoes on this site go back, I think, 2 to 3 million years, and the current pointy symmetrical edifice is just the youngest edition of volcanoes on this site. There's a few others in the neighborhood which are extinct and are far, far older than that even.
So
in central Mexico, there's a lot of volcanoes for reasons I don't entirely understand.
Do you know, Andrew, when if this were to have a more major eruption, what type of eruption would it be? Would we have more like of a lava flow, or would we have more ash for the rest of the time?
It tends to like explosive eruptions, and also smaller lava flows generally confined to the crater, but it's mostly explosions. Like this sort of thing, like you're seeing here, just bigger. So a major eruption tends to go what we call Plinian, where it's a giant column of ash that goes many tens of thousands of feet into the air and leads to ashfall and pyroclastic flows, and can be quite dangerous to surrounding residents.
And do you know if there are people monitoring this volcano to potentially warn local communities of
Oh,
a
yes.
potential major
The
eruption?
last major eruptive episode saw 50,000 people evacuated from neighboring communities like Puebla here.
That's good to hear.
Yeah, the Mexican Volcano Observatory, this is the one they keep their closest eyes on. It is, I didn't include this picture because I couldn't find out who took it, but there's a great picture of Popocatépetl standing over the downtown skyline of Mexico City. So it's really not very far away at all and is in the range of hazardous ashfall. So they do keep a very close eye on it. It is a well-monitored volcano. Like this picture here comes from a little monitoring station on the rim of the summit crater. I think that's fun. I like well-monitored volcanoes.
Me too.
Speaking of well-monitored volcanoes, there was a good-sized, significant landslide near Mount St. Helens a couple weeks ago. Back on May 14th, the landslide originated roughly 2,000 feet above the Spirit Lake Highway, which is Washington State Route 504 that goes up to the viewpoints of the crater of Mount St. Helens. This is the helicopter view of that. It's a pretty substantial Earth movement. A lot of material got moved. And this was mobilization of debris from the landslide that preceded the 1980 eruption of Mount St. Helens. And due to the hot weather and rapid melting of a very deep snowpack, this loose landslide material just mobilized and flowed over the highway and probably damaged the roadbed. So they have to wait for the area to stabilize before they can do any significant sort of reconnaissance on what damage may have been caused. So it could be a while before we even understand how much damage has gone on. Just for comparison, here's Mount St. Helens here, landslide was here. This is Coldwater Lake, popular recreational area. And there's a tunnel that goes from Spirit Lake to right where this landslide happened. And they use this tunnel to drain Spirit Lake to make sure it doesn't overflow the ash and maybe cause a catastrophic failure, which we know has happened in the geologic record. They wanted to avoid that after Spirit Lake got moved during the 1980 eruption period. And so this tunnel goes right down there, and the landslide did damage the exit of this culvert, which is up here. Obviously, there's still a lot of water flowing out of it, so there's, no, they're not worried about any catastrophic failures anymore. But this is an interesting area, and I will certainly keep my eyes on updates from this.
We have Paul was curious if this landslide cut off access to the visitor center.
Yes.
Yeah.
They closed the highway here at the Mount St. Helens Institute Coldwater Learning and Science Center. So highway's closed here. So Coldwater Lake and the Hummocks Trail and Johnston Ridge are all inaccessible for the foreseeable future.
And any updates on the people that are trapped on the other side?
Oh, yeah. They got helicoptered out. I forgot to mention
Good.
that. They were there, and then they got a helicopter ride to somewhere where they could get picked up. As far as I know, their cars are still in the parking lot at Johnston Ridge and will be for a little while. Kind of an interesting way to lose access to your vehicle. All right, on to some research topics. Some interesting science has come out recently. This is the one that got me most excited. The International Ocean Drilling Project, or its Ocean Discovery Project, now they renamed it a few years ago, is a global initiative to drill the rocks of the ocean crust to try and understand different geologic processes. And this ship, JOIDES Resolution, is a research drilling ship. I have no idea what Joint Ocean Initiative for Drilling Environmental Ship, I think is what that stands for. It's a long acronym. But this is a research ship that goes around and drills rock cores out of the ocean floor. On this particular expedition, they were drilling cores from an undersea volcano near the mid-Atlantic ridge in the center of the Atlantic Ocean. And then one of these cores of rock, 1 kilometer long core of rock that they pulled from down turned out to be mostly peridotite and serpentinite, which are the rocks of the lowermost crust and the uppermost mantle. So these are the freshest and deepest rocks we've probably ever recovered from a vessel like this. And this has been a target for researchers since the early 1960s because we have samples of mantle that get blasted up into volcanoes sometimes, but fresh, intact rocks from the mantle are something we've been chasing for a while, because that will help us understand how crystals fractionate, how crystals form, what minerals are forming in the mantle, and most interestingly, in this context, how are these rocks interacting with seawater? Because of where they drilled this from on the mid-Atlantic ridge, the ocean crust is only a couple kilometers thick. So they got through that into the uppermost mantle before it got too hot and they had to stop the drill. Those rocks are generally a thing called serpentinite, and they react to seawater to create hydrogen and organic compounds. And these are the things, if you've ever heard of black smokers or other undersea water vents, there are these big columns that are spewing out superheated water that is just full of minerals and organic compounds, and probably one of the places where life originated on this planet many, many billions of years ago. So understanding the chemistry of those rocks as recovered from where they live basically helps us understand the chemistry of the origins of life in the deep sea. So very interesting, huge implications from this kind of research. Very interesting. Questions about that?
Yeah, do we know if this is what they were going out and drilling to find?
They
If
were
they
not.
looking for
This
the
is
quartz?
something they
Oh.
picked up. They sort of said, hey, we're in the area, might as well give this a shot. They were looking at this undersea volcano in that area, which is one I'd never heard of.
And then do you know the process of getting a core from an undersea volcano? Is like, how do they do that?
It's a dead volcano, so it's not pulling up magma or anything.
Yeah,
It's
but just like
a,
from getting a core under the ocean. Do you know how they do that?
the same way they do it on the surface. You basically, your drill bit is hollow, and as it drills down, it keeps the center part intact, and then you pull it up. The specific mechanics of that are not known to me.
Can I say something on that?
Please.
Okay, Bill Orr is going to be our speaker in September, and he was on the Glomar Challenger, which was the first drill ship that drilled the ocean floor. And he'll talk about dynamic positioning. In order to drill on the ocean, you have to keep this ship stable and from drifting. And he'll talk about that. So be sure that you join us in September.
Very
Sounds
cool.
great.
Yeah, I'll
Thank
make
you,
sure to tune
Sheila.
into that. So I attended the GSA Cordilleran meeting a few weeks ago, which was in Reno, and the most interesting and I think pertinent research that was presented was about these major floods that impacted Death Valley National Park and a lot of California, frankly, at the end of last year and the beginning of this year. And these major floods came from storms that dropped probably a 1 in 500 year storm on some of these mountains up here in particular. But fortunately, there's been a decades-long project by a number of geomorphologists to understand how these canyons and these dry washes act during storms. How is sediment moving? Are they eroding? Are they filling up? And how is that changing from place to place? So they've been looking at 3 or 4 major popular canyons in the Death Valley area. And these big storms hit, and they think, great, perfect. These are huge storms that don't happen very often. We'll go and do some research and see how things happen. And they found out that these enormous floods that dropped several feet of rocks and gravel many miles away from the mouths of the mountains, basically there was minimum to no impact in the upper reaches of these canyons. So where did this sediment come from, and why didn't it come from the canyons? I don't know. So these canyons will show net deposition in a lot of storm years like this. This year in one of the canyons they looked at called Mosaic Canyon, That was net 20 centimeters of erosion, so it's about this far. Whereas since 1993, about 8 feet of gravel has been deposited in that canyon. So the floor of that canyon is really hard to, you can't see it at all now because it's under 8 feet of gravel. And this is the largest flood that's come through there in a long, long time, and it did this much erosion. So that's weird and interesting, and is a matter that these geomorphologists are contemplating as their research in this field goes forward.
So you're essentially saying that in the canyons up in the mountains in this picture up here, where
Yes.
the lowlands are, there's not a lot of erosion, but there's a lot more deposition happening in the
Generally,
actual
yeah,
valley.
which is
So
interesting.
is it possible they're coming from the highlands, like above the canyons, or is that also, did they also look at that and say there's no erosion in the highlands too?
Well, that was the weird thing, is that the canyons were, I mean, basically.
Oh, the whole thing, the whole mountain.
Yeah, so there's obviously a ton
okay.
of deposition down here on the flats.
Mhm.
But like these canyons up here, right in this dark area, is the kinds of
Mhm.
areas they were looking at. Very little change from this enormous floods.
Okay. Thanks for clarifying that. That's crazy.
Yeah, it surprised Alan Glasner too. he was pretty perplexed by that. All right, Antarctic megaslides. Over the past couple of decades, Antarctic seafloor researchers, which is apparently a whole field, have been studying these massive underwater landslides that ring the Ross Sea in particular here on the, I was going to say the north coast of Antarctica, but all of Antarctica has a north coast. There is no south coast in Antarctica. But a lot of these undersea landslides are more than 100 meters thick, sitting up above the bottom of the seafloor. But right below these slides, which they discovered through the ocean drilling program, they found out that underneath these landslides were these layers of organic rich matter. Really crumbly, really weak, really slippery, organic rich ocean rocks. And as time went on and glaciers deposited sediment on top of that, and general ocean floor sedimentation piled more and more material on top of these, eventually these slopes failed, probably during earthquakes or some other kind of major energy event, whatever that might be, sending these huge landslides out across the ocean floor and probably sending tsunamis all around the Southern Ocean. They found out from these rocks that at that time, the climate was about 3 degrees warmer than current. So this is a couple million years ago that these were from. They did not give an exact time, but through the isotopes, they were able to tell that this is a roughly 3 degrees Celsius warmer period. That's for ocean temperatures. And that allowed these really brittle layers to form. And since we're cruising towards that threshold with definitely within 100 or 200 years, there's interest growing about could these layers form again, and are they likely to present oceanic tsunami hazards? So this paper just presented the presence of these large landslides and their causes, which was this organic rich mud layer, and wants to raise questions about, okay, we need to look at this more to see if this is something we should be worried about in the future. Any questions about that?
Yeah, this is not on the chat, but I've got a quick question on this. This is from our standpoint here in Central Oregon. A lot of our slip plains and in the deep-seated landslides in the Coast Range are clay related. Were they indicating that these organic rich layers were siltstone clay mineral composition in addition to the organics?
Yes, they were silty clay, generally with a very large organic component.
In other words, whoop, slip plains.
Very slippery.
Thank you.
Yeah. And that's all the research and news I've got for this month. I will see you next time. Thank you very much for listening. I'll take any other questions you may have.
No, not from this side. Thank you,
All
Andrew.
right.
Thank you for taking the time with your busy week.
Yeah, we really appreciate it. Well, I'm going to pass the baton to Dr. Paul Shea, who has been with us, I think, almost since the beginning. And we had another wonderful presentation from him last year, but Paul was kind of hiding his light under a bushel about some of the work that he's done in the past, or at least I hadn't looked deeply enough at his CV. So he's going to talk to us today about some pretty fascinating work with the oil spill disaster that we remember from, was it 2010 or 2011?
2010.
2010. All right. Well, Paul, I'll let you share your screen and take it away.
Thank you for having me. And, I'll just start by saying that, maybe once in a career, you get to do something that's like way out in left field, something that you'd never expect to be involved in. And for me, it was getting involved with the Deepwater Horizon oil spill. So this is an experience that I would like to share with you. So Deepwater Horizon is actually the name of the offshore drilling rig. And in 2010, it was operated by BP to drill the Macondo well, which is at this yellow dot here in the Gulf of Mexico. So if we zoom into this area, the coast is here. Houston is here, New Orleans is here, then we have the continental shelf and the slope, and then we get down to the deep basin here. So the Macondo well is just right at the end of the down slope side of the slope, and it's pretty much at the mouth of the Mississippi River. So the rig sits, here's a picture of the Deepwater Horizon drilling rig. It sits on 5,000 feet of water, and the oil reservoir is actually 13,000 feet below the seafloor. So the rig is actually 18,000 feet from the reservoir. So, you talked about positioning a drilling or a ship or a rig, this is some really high-tech stuff going on here. At the top of the well, there's a instrument called the blowout preventer, the BOP. This is not to scale, obviously. And it's a series of hydraulic rams that is supposed to clamp the riser pipe shut in case of a blowout. Unfortunately, this didn't work, and a blowout did occur on April 20th, and causing an explosion. 11 workers died. And 2 days later, the Deepwater Horizon drilling rig collapsed and sank into the ocean. So in the succeeding couple of months, BP tried to use various methods to either stop the oil from coming out of the well or capture the oil, but none of those succeeded. So for example, after cutting the riser pipe and oil was just coming out at the top of the blowout preventer, BP tried a device they called the top hat, which is supposed to fit on top of the of where the oil was coming out to try to capture the oil. However, this didn't work, and one of the reasons was that the initial estimate of how much oil was coming out was way too small. So the BP had estimated that maybe 10 to 15,000 barrels per day of oil was coming out. And in the end, when we did the analysis, it was more like 50 to 60,000 barrels per day. So basically, after about 2 months, none of the methods that tried to stop the oil from coming out was able to prevent polluting the Gulf of Mexico. So on May 10th, this is about 20 days after the spill, President Obama directed the Secretary of Energy at that time, Stephen Chu, to form a government science team to oversee the BP source control effort. So here's Secretary Chu, and Secretary Chu has had a group of senior science advisors, which included, they are all like internationally known scientists. This is Tom Hunter here, who was a former director of the Sandia Lab. Here is Marcia McNutt, who was the, at that time, the director of the U.S. Geological Survey. Admiral Thad Allen, you probably remember seeing him on TV. He was the incident commander, so he was like the overall kind of top level decision maker at that time. So underneath these senior officials were this group of scientists and engineers whose job was to kind of do the type of analysis that was needed to help make decisions. So by July, all the efforts to either stop the oil from coming out or capture the oil had failed. So finally, it was decided to put a cap on top of the well. So the cap is actually a huge device also that would be mounted on top of the blowout preventer. And this would provide a way to finally stop the oil from coming out. Unfortunately, there are hazards associated with this. And to understand the hazards, we have to kind of look a little bit at the geological setting of the Macondo well. So here is kind of the schematic stratigraphy. Basically, we have layers of shale and sandstone starting from the ocean floor 5,000 feet deep all the way down to the oil producer reservoir down here at 18,000 feet. So if this was a column of water, then the water pressure would follow this purple line, which is labeled hydrostatic. However, because this is a subsiding basin with these layers of shales trapping pressure into here and then more sediments coming in, much higher fluid pressure is built up into the sediment. So the actual pressure is this black line, which is labeled pore pressure. So this is actually the pressure in the sediments trapped in this column, which is significantly higher than hydrostatic. Now, the most critical pressure profile is this red line, which is the fracture pressure. So the pore pressure gets up to the fracture pressure, that will cause the sediments to fracture. So in fact, when an oil well operation, does hydraulic fracturing, what they're doing is to inject fluid, build up the pressure until we meet this fracture pressure, and then the sediments would fracture. So in this type of environment, the natural pore pressure that's trapped in the sediment is actually very close to the fracture pressure already. So to drill a well in this kind of setting, you have to kind of drill it in stages. So first you drill a really wide hole, then you put a casing in, cement it in, drill another, and then inside that drill another section, put a casing in and cement it in. And you need to do that so that the higher pressure at the lower depth won't come out and cause fracturing in the shallower depths. So the well itself is actually constructed by a nested set of casings. And in order to prevent high pressure from being trapped in here, there are these valves, they're release valves, they're called rupture discs that are set into these casings so that in case there's a high pressure trap, the valves will open and letting the pressure out. So the BP engineers were afraid that during the explosion, some of these rupture discs had failed or collapsed, and basically then you have these open sections in the casing. And if we close the well, then oil can leak out of these failed ruptured discs. So the thinking looks something like this. As long as the well is open and flowing, then the oil pressure in the well follows this light blue line and is significantly below the fracture pressure. So that's fine because the well is open at the top and no pressure can build up. Oil is flowing out of the well into the Gulf of Mexico. Now, if you cap the well, the pressure will start to rise because its bottom pressure is going to try to get back up to the pressure in the reservoir. And as the pressure climbs, you can get to the point where the oil pressure meets this fracture pressure. And if these ruptured discs are open, the oil can leak out. And when that happens, a hydrofrac will develop and grow up towards the seafloor, and you'll get something called an underground blowout. And this would be a catastrophic development because it would be very hard to control and stop such a blowout. And you can run the risk of having this blowout occur for years and draining the entire oil reservoir.
Paul, before you move on, could you go back 2 slides to that chart? Because we had a question from Paul Edison Lamb about that weird little squiggle at the bottom, just above 18,000. Could you explain why that's happening?
Yeah, that is where the oil reservoir is located. This diagram is a little off, but and why the pressure, there's a reversal in pressure. I can't give a clear explanation of it, but that happens.
Okay, thank you.
Sorry, I couldn't get into every detail of each graph here. Okay, so I was asked to be part of this well integrity team, which is formed by scientists from DOE labs such as Lawrence Livermore, Los Alamos, Sandia, and also the USGS. And the goal of this team was to evaluate the risk of an underground blowout if the well is shut in, and also provide guidance for how to evaluate the shut-in if we were to do that. So I spent part of the summer in Houston in the BP office. They put aside a certain space for the government scientists to work. And basically our days are meetings with BP engineers, government officials. We get assigned tasks to do analysis, and then we go back to our own workspace and do our analysis and come back for the next meeting. And then this was just go on and on pretty much around the clock. And sometimes we're so busy, we don't have time to go back to our motel, to go to bed. So we basically lived there. So by July 11th, we came up with a set of criterion, which is on how to evaluate the shut-in if it were to happen. So basically, we want to look at the pressure in the well cap. If the pressure is low meaning 6,000 psi's or less, that means the well is not holding pressure. That means there must be a major leak and the well was damaged, the ruptured disc had failed. And if that's the case, then we must actually reopen the well and let the oil flow again after 6 hours, because if we keep the well shut in, then we run this risk of this underground blowout. So conversely, if the pressure is high, that means the well is holding pressure. That means that the potential for a leak is very low. We can run the test for a much longer time, 48 hours, and probably keep the well closed continuously after that. Then there is this uncertain zone because the analysis is not exact. If the pressure is between 6,000 to 7,500 psi, then there may be a leak. There may be something that our analysis, the assumptions might not be totally correct. And this is kind of the big question zone. And the decision was, if we're in this zone, then a decision had to be made after 24 hours, whether to keep the well shut in or open it back up to prevent a hydraulic fracture from happening.
So Paul, just curious, and you might be covering this later in your presentation, so feel free to just say that, but since 2010, have there been projects looking at what they're going to do if they have to open it up, ways to capture the oil or any other solutions? Do you know about that?
Well, basically the solutions are there, but takes time. So the way to actually finally kill the well is to drill a relief well to intersect the original well at the bottom of the well and then inject cement into it. But that relief well was not going to be done until September. So we have a couple of months where we have to, if you don't want to run this risk of an underground blowout, you have to let the well flow.
Okay, so a bit of a
Yeah.
spoiler that we're not still looking at these risks right now. This was like a project for in the interim before they had a more permanent solution.
Right.
Okay, gotcha.
And Paul, there was a question, and I know some of us have dealt with this in our careers. Were there trade secrets or other proprietary interests that interfered with you guys being able to run your evaluation?
No, we basically had an agreement with BP to access their data, but we couldn't publish it or something like that. But while we were working with them, we pretty much had access to whatever data we wanted. Okay, so July 15, the shut-in begins. The shut-in started around noon. So you don't shut the well, the oil flow all in one step. You kind of slowly reduce the flow in 10 different steps with some hold period in between so that you don't kind of create a shock to the system. So at about 1:30, the pressure in the capping stack, this is maybe the flow was reduced by maybe a third, is kind of in this just over 4,000 psi. 140, it rises. 150, we're about halfway closed now. And at 2 o'clock, we're at least out of the high leak zone. So we're now in the medium zone. This is now, maybe 2/3 closed, 210, 220, full shut in, and we're in this zone, still waiting. Wait until 6 o'clock. It's not going to go up to this low leak potential zone. So we're stuck right in the middle of this uncertain zone where we are not sure if the well is still intact or it's leaking. And so the protocol is that within 24 hours, we have to make a decision. So the factors to be considered, the government kind of operates on this abundance of caution idea. So with the abundance of caution idea, we would not run the risk of an underground blowout and reopen the well after 24 hours. And in fact, almost everyone in the government science team felt that that was the thing to do. However, there was an additional set of data, which is the pressure that was obtained during shut-in. That is often used for additional analysis. So the question was, can this shut-in pressure be analyzed to get more information? And I was the modeler in the government science team, so that assignment was handed to me. So by then it was, nighttime. The decision had to be made the next day. So basically, I had to pull an all-nighter to this analysis. So there were kind of three challenges that I faced. One was I had to get the data. Next was I needed some modeling software to do this oil well modeling, and there was very limited time. So, the only way to get me the data was I was actually in California at that time because I had some family obligations, so I came home. So my colleagues in Houston just took a picture of the screen on the monitor and sent me that picture. So that was my my data. So these two green and blue data points are the pressure in the cap in the well cap at kind of slightly different elevations, and you can see how the pressure rose as the well was shut in, and then once full shut in was achieved, it kind of flattened out. So for modeling, I, being a hydrologist, do water modeling, but if you kind of know what's under the hood of a groundwater model, it can actually be kind of tweaked to do oil well simulation. So that's what I had to do because I didn't have an oil well simulator. So I used the USGS model ModFlow. And then finally, I had only time to look at kind of a limited number of scenarios. And I quickly realized that one scenario to look at was what is called aquifer support. So initially, the BP engineers felt that there was water surrounding the well. So if here is, an anticline and with oil trapped under some low permeability layer, if there's water surrounding the well, then the water would help maintain oil pressure as the oil is depleted. However, the presence of water is kind of really iffy from geophysics. So one of the scenarios I looked at is, what if there's no water support? This is just kind of low permeability material with this oil trapped in here. And it turns out that if you run a model with no aquifer support, with a well that is intact with no leak, you can simulate the data that has been recorded fairly well. I didn't exactly simulate each step of the shut-in. I just kind of simulated the style, but it turned out that you can find a credible scenario that can explain the data. So the next day I wrote that up, presented it. And so in a way, my job was done. So the hero of the story is really Stephen Chu, because he had to decide what to do. And so if we continue the shut-in, obviously we have no more oil release. And this can be supported by a reasonable scenario that the oil is not leaking. But if we were wrong, the consequences of an underground blowout is catastrophic. So Stephen Chu, what he did was he said, okay, let's continue the shut-in, but we'll deploy an extensive monitoring system to detect leaks. And we'll update our reservoir model as we get more data and review everything every 6 hours. And then later it was extended to every 12 and then every 24 hours. And at the first sign of a leak, the well will be reopened. So that was the strategy to go forward, and it turned out to be the correct strategy. So some of the monitoring involves seismic monitoring, where every day they'll do marine seismic to look at reflections from layers, and we'll compare the seismic data from one day to the other. And if oil is leaking into strata, there will be a signal that can be detected. And also there were sonars monitoring the water column for possible bubbles coming out of the seafloor, which would be an indication that there's oil coming after the bubbles, and various other monitoring. And we also updated the reservoir model. So this was the model projection after 6 hours of shut-in. And after 1 day, the projection was still pretty good. And this was assuming the reservoir is kind of this extensive reservoir. But after 2 days, we are no longer simulating the data. After 3 days, way off. And if we had extended it to 19 days, we'll be way off. So we brought in an expert in sedimentology, and he says, well, these sand bodies are not extensive. They're actually channels. So you should change your reservoir model. And once we changed our reservoir model to kind of a channel, we were able to explain, the observed data. So after 19 days of monitoring, there was no sign of leakage. The reservoir model was able to simulate the shut-in pressure. And so that gave the entire team confidence that the well was intact. And on August 3rd, mud and cement was pumped into the well from the top to stabilize it. And then finally in September, the relief well was drilled several kilometers from the original well and then angled to intersect the well. And then cement was pumped in from the bottom to finally seal the entire well. So the total oil discharge was about almost 5 million barrels, of which a little less than 1 million was recovered. The flow rate, as we estimated this, was somewhere between 62 and 53,000 barrels per day, this being the largest offshore oil spill in US history. So just some concluding comments. We as geoscientists often work on projects with timelines that extends over months or years. But in a crisis situation, the response time is much shorter. And in the Deepwater Horizon situation, basically we have hours to do analysis, and the analysis that we did during the day was explained by Admiral Allen to the TV crew in the evening for the evening news. So basically, you need a very high level of coordination between engineers and officials, have ready access to data, able to mobilize people and try to adapt whatever technology that you have available, to use, because there's no time to develop new technology. Thank you.
Oh, Paul, that was delightful. We did have one, whoops, just about lost it here in the chat. One question about the repair. Could an earthquake disrupt this repair?
Well, I think earthquake was not a hazard in this particular situation. But I suppose that if you're drilling in an earthquake area, an earthquake could cause all sorts of hazards.
Yeah. And then another question came up is, how near to the site was that cap built? Did they have to fly it in or move it in from somewhere way parts far away from the Gulf?
I'm not sure, but my guess is since the main operation of BP is in the Houston area, they probably have that cap, either assembled close by. But on the other hand, ships were coming from, all around the world for this to support various types of operations. So it was almost a global kind of situation.
We're right at our hour at the noon hour. So I'm going to thank Paul. We're going to turn off the recording. People who want to stay and ask questions, we don't expect anyone to have to stay in your seat for more than an hour. So you're all free to go, but I think we will keep the room open for the next half hour if there are further questions for Paul.